Okay guys, we are finished with unit 1, 2 and 3 of chapter 3, if I am correct. Yep, chapter 3. I'm going to go to unit 4 now, then we're going to go to unit 5, then do unit 6 because unit 5 and 6 are very much the same. So I'm going to speed run this, I'm going to see how fast I can do this. You guys can play the video over and over again, you guys can put in slow motion. Fast forward if you guys think I'm going too slow. So I'm going to quickly go through it. I'll explain to the best of my abilities and you guys can just follow along in your books. So we're doing gears right now, unit 4, page 52. We're now at gears or wheels with cogs, also called teeth or spurs. So you guys must please know this. This is the definition of a gear. So a gear is a wheel with teeth on it. It's as simple as that. The cogs are shaped like wedges. It doesn't matter what they're shaped like. It can be shaped like triangles or like that, or normal squares. It doesn't matter what the shape is, but a gear cannot work by itself. There we go. That's a key information right there. It has to have more than one gear to work. So there's 2 gears over there. Here's a hand. There's a whisk over here, a hand whisk. There's 1 gear over here, and there's a little small gear right over here which you can't really see. There's 2 little small ones over there. So it always works in pairs, 2, 3, 4, 5, but never alone. Its teeth must interlink with teeth on another gear, like right over here in the picture. You have two gears and both of their teeth mesh with each other. So when gears are linked, we say that the gears are meshed, like I just said. When the teeth interlink, then they are meshing together. So gears are mounted on axles that are called the shaft. So this long piece of metal right over here is the shaft, which the gear is attached to. Just like how we learned over here, how a car's wheel is attached to a shaft over here. Just like that, the gear is attached to the shaft. So now this paragraph over here is just explaining this figure 3.24, the hand whisk. So we're going to skip that. I'm going to go right over here to the counter rotation of gears. And you guys can put 2 and 2 together. So if a gear turns this way, the counter rotation is the opposite direction. So this is clockwise and this is anti-clockwise. So right and left, they just go different directions. So when the driver gear turns clockwise, its teeth push down. So let me see if I can draw a picture of it. Here's the driver gear. It's turning clockwise. So these teeth over here on it are pushing downwards. The teeth push down on the driven gear's teeth. This causes the driven gear to turn into the opposite direction. So the teeth push down on the driven gear's teeth, and that causes the gear to turn as well. So in anti-clockwise direction, but it can be anti-clockwise or clockwise, depending on which direction your driver gear is moving. So we say the gears counter rotate. When they go opposite directions, they are counter rotating. A pair of gears will always counter rotate. And the emphasis on the word pair. Pair refers to, right over here I put over here 2G. So it has to be 2 gears. Only 2 gears is a pair. So if you have 2 pairs, then that will be 2 gears. So if you have then 4 gears, they will all counter rotate. 6 gears, they will counter rotate. So it's always even numbers, 2, 4, 6, 8, 10, 12, up until infinity. It has to always be even numbers for the gears to counter rotate each other. So we aren't going to do the enable task 3.5. If you want to, you can go do it at home. But it's a practical activity where you physically go and make a gear. But I don't think that is really needed. So we're going to carry on to page 53. So now using, right over here, page 53, using other gears to synchronize the rotation of gears. So here in 52, you saw that a pair of gears always counter rotates. But what if you want to synchronize the rotation? So you want it to be the exact same. So you want the driver gear, which is going clockwise, to go the same direction as the driven gear, which is also going clockwise. So the way we do that is, you'll see over here, there's an idle gear in the middle here. let's quickly read over here. The only way to make the driven gear turn in the same direction as the driver gear is to put another gear between them, right over here. The only function of this extra gear is to change the direction of the driven gear's rotation. So that's the only function of it. It doesn't change the speed, doesn't change the velocity, doesn't change the turning force. It just changes the direction of the turning. So clockwise, clockwise, stays the same. So this type of gear is called the idler gear, like it's labeled over here, the idler gear. And the size of the idler gear does not have an effect on the velocity with which the driver or driven gears rotate. Like I said already here in the previous sentence, it is to change the direction of the driven gear's rotation. That is the only purpose of the idler gear. There is no other purpose for it. So that's why it says over here the velocity doesn't change. So since this is the only purpose of the idler gear, it just changes the rotation. So to save space, idler gears are often very small, because it doesn't matter how big or small it is, it just changes the direction. So you want to try and save space, make it as small as possible, save money, save costs. So when an idler gear is small, it rotates much faster. So usually if a gear is bigger, it'll rotate slower, and if a gear is small, it'll rotate faster. Now since idler gears are made smaller to save money and to save space, it spins faster than usual. So this means it wears out much quicker. So it rotates much faster than the other gears, and it wears out much quicker than the other gears. So since it's rotating faster, it wears out faster. So therefore an idler gear must therefore be made from a harder and stronger material. You guys must please know this. So the idler gear is made of a stronger metal than the driver gear and the driven gear, since it wears out faster. Page 54. Velocity ratios and force ratios. So gears can be used to change the velocity ratio and the force ratio. So the velocity ratio is the distance it's traveling. So it's if it's going faster or slower. And the force ratio is how strong the gear is. So using gears of different sizes to change the velocity ratio. So I'm going to quickly show you a summed up version of page 54, 55 and 56 right here in one drawing. So here's the drawing I already made for you guys. So the velocity ratio, all you do is just read what it says over here. So I'm now at the bottom of page 54. When the driver gear is larger, right over here, the driver gear is larger, it's bigger than the driven gear. The gear system is used to increase velocity. So here, right over here, velocity ratio is increased velocity. So therefore, you can put 2 and 2 together. Now, if the driver gear is small and the driven gear is bigger, then it decreases velocity. So like I said, the velocity ratio increases the amount of distance it travels. So you'll see the reason why the velocity is increased, so that means the distance it travels is increased. If you have a big gear, if it has 50 teeth and this one has 10 teeth, this gear just needs to turn 20% for this gear to turn 100% all the way there. So out of the 50 teeth, only 10 out of these teeth needs to turn for this whole gear to turn. And this distance, which is only like a few centimeters, then goes all the way around this whole gear, and that's why the distance is increased, the velocity is increased. And the same goes for over here. This whole gear, let's just say this is 10 teeth and this is 50 teeth. This gear must turn 5 times for this one to only turn once. So the distance this thing is traveling is decreased. So therefore the decrease in velocity. So let's quickly go back to the page over here. There is an increase in velocity because the driven gear is much smaller than the driver gear, like I've already said over here. So when the driver gear is large, it has more teeth than the driven gear. For every one turn of the big gear, the small gear turns several times. So if this gear turns once, this one turns 5 times. I just gives you a little example over here. This one right over here. So the velocity is also depending on the amount of speed it has as well. The amount of speed per second. So right over here, I'm pretty sure it's not going to show you guys now in the book over here, but velocity is measured over here. You guys can write it down if you want to know it. You guys won't use it now during this technology, but velocity is the amount of meters an object travels per second. So if this thing if this thing moves 50 teeth, then this one travels 5 times around in a circle. So it goes faster, which is the speed of it, which is in seconds, and it's also traveling at more distances. So that's the meter part. So therefore the velocity is increased, so the distance it travels per second is increased, and that's why it's increased in velocity. And this is just something you guys must know. It's just something you guys must know. There's no way around it. There's nothing special about it. Just like how you guys learned 1 + 1 = 2, this is how you guys will learn that this is and how to increase the velocity. So if there's an exam question where it asks you how can you increase the velocity of a car's wheels and something, then you can just say increase the driver gear's size, decrease the driven gear size. It's as simple as that. So this last paragraph over here on page 54 is what I just showed you over here. The driven gear is large, the driver gear is large, and the driven gear is small. So therefore the velocity is increased. Velocity is increased over here, and vice versa. The driven gear is small, and the driver gear is small, and the driven gear is large. Therefore the velocity is decreased, like I've already showed you. And this last little paragraph over here isn't really any useful information which I will ask you in the exam, so we can just leave that out over here. Now we can carry on to page 55, how to calculate the velocity ratio. Very easy. So the velocity ratio, also called the gear ratio, shows by how much the velocity increases or decreases. So we want to figure out if the velocity increases or decreases with specific gears. So when the driven gear has fewer teeth than the driver gear, the velocity is increased, like we've already seen over here. The driven gear has less teeth than the driver gear, so the velocity is increased, and vice versa. And velocity ratio, guys, is a good thing. You want it to be nice and large. So if it's 1/1, then it's 1. So 1 gives you no benefit at all. But if it gives you any number which is bigger than 1 and bigger, so 1.1 is bigger than 1, so there we go, it increases. And the bigger the number is when you get your final calculation, the more velocity is increased, which means it's the mechanical advantage has also increased as well. And the same goes for the decrease in velocity. If it is less than 1, then the velocity is decreased, therefore the task is more difficult, therefore the mechanical advantage is also more difficult. So the velocity and the mechanical advantage goes hand in hand. You always want it to be positive, bigger than 1. And here we're going to learn how to calculate it. So the velocity ratio will be greater than 1 if the driven gear has 12 teeth and the driver gear has 24 teeth. Like we've already said, it's bigger than 1 because the driver gear has more teeth and the driven gear has less teeth. So let's quickly make the sum over here at the bottom of this page. You guys must please know how to calculate this for the exams. Velocity ratio, VR, means velocity ratio equals the number of teeth on the driver gear divided by the number of teeth on the driven gear. You see over here, it's the exact same. If the driven gear has 12 teeth and the driver gear has 24 teeth, the velocity ratio, VR, is 24 divided by 12. See, there we go. Driver gear teeth divided by 12, which is the driven gear teeth, equals 2. And 2 is bigger than what 1 is. Therefore, the velocity is increased and the mechanical advantage is also increased as well, which makes it easier for us to turn the gears. And it goes vice versa as well. So you guys, it stays this every single time. You guys must just know which one is the driver gear, which one is the driven gear, but it'll tell you in the test or the exam, and it'll tell you how much teeth each gear has. So this is just plug and play. So if you have a driver gear which has 60 teeth, and you have a driven gear which has 20 teeth, then the velocity ratio equals 60 divided by 20 equals 3. And since 3 is bigger than 1, the mechanical advantage is increased as well. And that is basically what this whole paragraph is right over here. And it goes vice versa as well. So if the driver gear had 20 teeth and the driven gear had 60 teeth, then it would be 20 divided by 60, which equals 0.333 repetitive forever. And 0.3 is less than 1, therefore the velocity is decreased and the mechanical advantage is also decreased. Now we're going to see using gears of different sizes to change the force ratio. So I'm going to quickly skip to page 56 because here is a very nice summary of it. Out of here, the force ratio right below these few questions over here. So that's why I actually have I still have this open over here. This is for the force ratio. So when the driven gear has more teeth than the driver gear, the driven gear has more turning force. So the driven gear right over here, so here's driven, driver. When the driven gear has more teeth, 24 and 12, has more teeth than the driver gear's teeth, then the driven gear has more turning force. So more turning force. That's a F, not a V. And I'm gonna assume that it's the same for this top one as well. If the gears is bigger, then it will have a more turning force. And the force ratio will be greater than 1, which equals less velocity. So when the driven gear has fewer teeth than the driver gear, the driven gear has less turning force. So yes, it is correct. So if the driven gear has less teeth, then there's less turning force. Therefore, the driver gear has more turning force. So I'm gonna base all these words now over here based on the number of teeth for the driver gear. So when the driver gear has more teeth, the turning force increases. The same goes over here. Now, if the driver gear has less teeth than the driven gear, the turning force decreases. So now you guys can go see over here, it matches up. If the driver gear is smaller, there's a decrease in velocity and a decrease in turning force. There's an increase in velocity over here because the driver gear is bigger, therefore the teeth are also bigger, therefore the turning force is also increased. And now you guys can literally go and pause this video right here, and this is all you need to know for the gears right here. So now I'm quickly going to go through this activity. So these 3 points over here I've already discussed. The -1, +1 equal to 1. It just shows you the velocity ratio and the mechanical advantage of it. So now we're going to go to this enabling task 3.8. It's very easy. I've already answered it here in pencil, but it's in Afrikaans. But I'm just quickly going to go through it with you guys as well. Complete each sentence. So when a small driver gear turns a large driver gear, it applies a what turning force? You just could check over here in the video previously. If the driver gear is smaller, when the small driver gear turns a large driven gear, and the turning force decreases. The driven gear turns in the driver gear, so the driven gear turns slower than the driver gear. The velocity ratio is then decreased, but the force ratio is also decreased. And you guys can now carry on with these questions. They all say the exact same. If the first word is bigger, then obviously the second word is smaller, and so on and so forth. So now we're going to go to Unit 5. Right over here, page 57. So Unit 5 and Unit 6 are very similar. They just explain how mechanisms can change the direction of movement using cams. So here's the one example using cams. The other one is using cranks. So cams are similar to wheels. They turn around an axle like a wheel does, but they are not round. So a cam is fixed to your what's the word I'm looking for right now? It's fixed to your shaft. There we go. Your cam is fixed to your shaft, just like your wheel is fixed to your shaft, but it's not round. So like over here, I just drew a picture over here where there's a purple line over here. This is where a circle would have been. So now it just has an egg shape or an apple shape or a pear shape, whatever shape you want. So here's the different shapes over here on the next page. It has a different shape to it. So when this wheel turns, it's going to push this cam follower, and the cam follower can be anything. It's over here is a stick. It can be a piece of plank. It can be a piece of wood, piece of metal. It pushes the cam follower up and down as you turn it. So a cam always operates with a cam follower. So here's a cam follower. Here's the cam. The follower can rest on the cam and gravity keeps it down against the cam, or you can use this plug over here. So there's a spring. So there's two ways with which you can keep a cam follower on the cam. There's two ways. So here's with gravity or with a spring to hold the follower against the cam. Cams can be positioned in different ways as shown in figure 3.31 to 3.33. So here's upright, then there's a little also like another shaft over here getting pushed up and down by the cam and the cam follower. And out over here is on the shaft, and there's a piece of, looks like a piece of metal, and now over here it's just faced sideways and it's making this thing go sideways left and right. But this stays linear, this stays linear, this stays linear, everything is linear. So cam changes rotary motion into reciprocating motion. You guys must please know this, that this is the purpose of cams. Cams change rotary motion into reciprocating motion, and reciprocating motion is forward, backwards, up and down, all in a straight line. As a cam turns, the cam follower goes up and down, or to and fro. So up and down, to and fro. The input motion is rotary motion, and therefore the output motion is obviously linear motion. So right over here, input is rotate, output is linear. Right over here, the last paragraph, cams can be used to create interesting movements. The shape of a cam influences the movement. So depending on what shape your cam is, it'll create a different type of motion. It'll still go up and down, it'll just create different types of up and down motions at different intervals. So now the rest of the paragraph is just showing you, giving you some information about figure 3.34, which we aren't going to need. So we're carrying on to page 58. You guys don't have to do this activity because it's drawing something, and we aren't going to do any drawing for this term. So we're just going here to this 1, 2, 3, and 4. The shape of a cam determines the movement of the cam follower, like I mentioned earlier. Now here is 1, 2, 3, 4, A, B, C, D. So here's 3.36, 3.37, 3.38, 39. And then it just explains to you guys the 4 types of cams, and you guys must please know the names. You guys don't need to know how they're used, you just need to know what their names are. This is the eccentric cam, which is this one over here, the snail-shaped cam, which is that one there, the pear cam, and the hearted-shaped cam. Those are the only 4 cams you guys must know, and you guys don't have to know what they work, how they work, because they all do the exact same thing. They all have the exact same purpose. So moving on, Unit 6, page 59. This is very much the same as what we just did in Unit 5. So crank systems that transmit a rotary motion. A crank system consists of 2 basic parts, a crank and a crankshaft, just like a cam and a camshaft, but now it's just a crank and a crankshaft. See, it's the same thing. The handle of a hand-operated beater is an example of a very simple crank system right over here, figure 3.40. The handle is connected to the crankshaft. Right over here, here's the handle. Here's the crankshaft. The crankshaft is connected to the crank, which is this giant circle over here, which has gears on it. In this case, the crank is the input gear of the beater, so right over here, the crank is the input. The crankshaft is the input. The crank itself is then the output of the crankshaft, but is then the input of these small bevel gears on the side of here, which makes your beater turn in a circle. So the crank system that is used for the handle of the beater transmits the rotary motion from the handle above the bowl to the rotary motion of the whisks in the bowl. This makes a task such as beating eggs easier or more comfortable. So there is 2 benefits of a crank shaft and a crank. So it makes tasks easier and more comfortable. So now we're going to go to this last paragraph over here. Crank systems that change the rotation motion into reciprocating motion. So right over here in this one over here, it's rotation, 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 rotation. Everything stays rotation. But now you can also go and make it into reciprocating motion, which is linear. So up, down, left, right. So figure 3.43 shows a crank system that changes rotary motion into reciprocating motion. A connection rod is connected to the crank. The connection rod goes up and down as the wheels rotate, and the crankshaft is the horizontal part around which the crank turns. So right over here, this part over here is the crankshaft. Well, actually, this over here is the crank. Here's the crank. So this, if you were to draw this now, it would just be a normal eccentric cam right over here. There's nothing special about it. And the connection rod over here is the crankshaft, which goes up and down. Very simple. We're almost done with this unit, which means we're almost done with the chapter. So figure 3.43 shows how Gr8 uses a crank system to create moving the wings for her toy penguin right over here. So here someone just used 2 crank systems, and right over here you can see here it's the same thing over here. There's the crank over here, here's the crankshaft, there's another crank, just like this previous one looks over here. So cranks change rotary motion to reciprocating motion, which you will already know. They can also change reciprocating motion into rotary motion. There we go, that's very important. So a crankshaft, a crank system equals both ways, and a cam system only goes one way. In a cam shaft, you can't take reciprocating motion, up and down motion, or left and right motion, and change it into rotary motion. You can't do that. But with a crank system, you guys can. The shape of the crank is often changed to make it stronger. So depending on what shape your crank is, it will be stronger. So now over here, you guys can come and do this enabling task 3.10, activity 3.10, page 60. It's very easy, it's just 3 questions. I'll quickly go through it as well. Both cam and crank systems change rotary motion to reciprocating motion, like we just said over here. Explain how the reciprocating motion of the 2 systems differ. So this is very, very simple. It's what I just said right over here. They differ because The crank system can do both. It can change rotary motion into reciprocating motion, and vice versa, reciprocating motion into rotary motion, but the cam system can only do the one of it. It can't do both of them. So that is how they differ. Question 2 over here. Crank systems can either be used to change rotary motion to reciprocating motion, or to change reciprocating motion to rotary motion. Can cam systems also be used both ways around? Explain. So like I just mentioned over here, it says in the book that the cam system can only do the one thing. But you'll see over here I wrote yes and no. So no, because it physically can't do it. But I also said yes, because anything is possible if you apply enough force to it. If you have a linear motion, an up and down motion, or a left and right motion, which is strong enough, which force is so strong that it can push anything, then eventually it can make your cam turn as well. But obviously you have to have a very strong up and down motion or left and right motion. It's the only way which will make it turn. But if your force which pushes up and down or left and right isn't strong enough, then obviously it's not going to work. So therefore you will say no or yes, and there we go, explain. So no because the book says so, and yes if you apply a strong enough force. Number 3 is Aisha works for a company that sends thousands of letters to clients. She wants to design a mechanical system that stamps the date on envelopes, and as this will make one of her tasks easier. Do you think she should use a cam or a crank system? Explain. So I would rate that she uses a cam system, because she won't need to move up and down motion into rotary motion. She just needs to change rotary motion into up and down motion into reciprocating motion. So therefore it's useless to use a crank system. Therefore use a cam system. That is all for Unit 6. Now here's Unit 7. Here we just learn how the graphical skills, drawing mechanisms. So we aren't really going to do that. It's just one page. So we aren't going to do that. So here you guys can just go now and do this revision activity. Question 1, 2, 3, 4. And also this checking your understanding of page 63. Question 1, 2, 3, and 4. Just those 8 questions. And as soon as you get to this challenge yourself, you can stop. But if you do want to do this, you can. But it isn't needed. This is all we're going to do. This is chapter 1 and 3 done. And in the next videos, we're going to go through chapter 4 and 5, which should be very easy. They're both similar chapters, so it should be very easy and all done in one video. Good luck with your revision questions.